Last time I had forgotten to say something. This is a small thing, but still it needs to be said. A definition of a partial limit. Is called a partial limit of a sequence xn if there exists a subsequence x and k such that limit of x and k equals So basically a partial limit is just a limit of some subsequence. Okay, and also last time I think I finished with the definitions of deleted neighborhoods. Am I correct? Deleted neighborhoods from the last time. Okay, so that was something from the sequences. Now we have our next topic, a limited function. In this lecture and sometime in the future, we will assume that our function is defined in a deleted neighborhood of the point in question. So let the domain of definition of a function contain some deleted neighborhood of point x 0. I don't specify exactly which deleted neighborhood, but some. This is x 0. Okay, now one of the most important definitions in this whole course. Definition. We shall say following Rasim. That the function f of x tends to a as x tends to x0, or same definition, but different words, or that the limit of f of x is and which right the limit of f of x as x tends to x0 equals a if for any epsilon greater than 0 there exists delta greater than 0 such that for any x from deleted delta neighborhood of x0 it follows that f of x is from a neighborhood size epsilon of a. Very important bit. This neighborhood is deleted, that neighborhood is not.
Epsilon, not delta.
Once again,
In this neighborhood, not epsilon, but delta.
this is delta, this is epsilon.
Ah.
I remind you, so here I maybe should have written it more explicitly, right? But let me fix it a bit. So I said it tends to A. I want to be explicit and say that A is a real number or infinity. Actually, we will like broaden a bit more this set of things that A can be, sort of symbols. But for now, let's have it just for extended relevant life. And x0 is also from the extended real life. If x0 is a finite number, then this expression we could write here like x minus x0 absolute value is less than delta but greater than 0. So I remind you that this deleted neighborhood is just a neighborhood without the middle point itself. So x minus x0, the distance from x to x0, should be less than delta, so it is inside the neighborhood. But it should, x should not equal to x0. So this distance should be greater than 0. Okay, and similarly over here we can write that if a is a finite number, then f of x is minus a absolute value of less than epsilon. Okay, so this is for finite numbers. Very well, very well, very well. Okay, so this is a definition of the limit of a function following cache. We will have a second definition of corrective function. Definition. A sequence xn is called a sequence at point x0 also if xn tends to x0, but does not attain x0. That means in quantifiers we can write that limit of x n equals x0 is 0 but for a natural n, xn is not x0. So this is the definition of any sequence. Now we have a second definition of a limit. Definition. We should say for k that the function f of x tends to a as x tends to 0. Yes. For a xn any sequence at x0 quantifiers, that would read that for any sequence xn such that here I'm given the restrictions on those sequences. Basically, this is those are the restrictions. Such that limit Sn tends to infinity of xn equals x0, but also for a natural, it follows that xn is not x0. So for any such sequence xn, it would follow that the limit of f of xn equals h. So this definition uses our knowledge about limits of sequences to construct a definition for the limit of the function. Okay. Note that here, everywhere here, I let number a and number x0 to be any real number or infinity. Also, I will later expand like this set of symbols that those letters could be a bit more. Okay, very well. So I once again remind you that all of this is under this assumption. The domain of definition of our function is contains at least some neighborhood of x0, delete neighborhood. Once again, I note that nowhere here we care about the value of the function at x0. So the function may be not even defined at x0 because we have a deleted neighborhood. Over here, we ask x to be from deleted neighborhood, so it should not be x0. And over there, xn should not be x0. So nowhere here we care about the value of our function at the point x0 itself. This is important. Okay, now we have two definitions of the same object. Now we want to see if those definitions are different. Third, about two definitions. Limit of a function f of x equals a as x tends to x0. Following Cauchy. limit of this function is a following a. So I'm going to prove that those two definitions are equivalent. So if some function has some limit according to one of those definitions, it has the same limit according to the other. Okay. Proof. Let f of x tend to a as x tends to x0 following Cauchy. That is, I'm repeating the definition following Cauchy. For a epsilon greater than 0, there exists data greater than 0, such that for a x from deleted data neighborhood of x0, it follows that f of x is from epsilon neighborhood of a. Let xn be a Haney sequence at x0. That is so now I'm going to write down this definition, but usually in this definition of a limit of a sequence, we used let epsilon as the number that is greater than 0. But now I'm going to use data, which is also like a legend. It's just some positive number. So I'm writing down for a delta greater than 0, there exists capital N such that for any N greater than capital N, it follows. Usually we write down that xn minus x0 less than delta, we would write it down. But here I want to write it as a neighborhood. So I will write down that xn is from neighborhood size delta of x0. And also noting that the sequence should not attain x0 over here, we can write here a deleted neighborhood. Deleted neighborhood, size delta of x0. Now, this number n depends on the previous numbers, specifically on delta, and I will denote it like that. We sometimes use this notation. It doesn't change anything, I'm just emphasizing that it depends on delta. Okay, let's go on. Now, for any epsilon greater than 0, I will take that delta from the Cauchy's definition. And for this data, I will take that number capital N delta from the Heine sequence. Such that for any n greater than that and delta, for any n greater than n delta, we have xn from this deleted neighborhood. For any n greater than delta, we have xn from this deleted neighborhood. And for any x from this same deleted neighborhood, we have that f of x from this neighborhood, from epsilon neighborhood of A. So we write, it follows that xn is from deleted delta neighborhood of x0, which implies that f of x is from epsilon neighborhood of A. So let's read this like that. For any epsilon greater than 0, there exists a number such that for any n greater than this number, f of x is from of xn. F of xn is from epsilon neighborhood of A. That means that the limit of f of xn as n tends to infinity is A. Hence, the limit of a function f of x as x tends to 0 equals A following A. So, I've proven this theorem one way. If a function has some specific limit following Cauchy's definition, then this function has the same limit following Heine's definition. Okay. Now we will prove converse. same limit following here. Yeah? So now I'm going to prove that if a function does not have limit a following Cauchy, then it would not have the same that limit a following here. So I proved that from the definition of the limit following Cauchy follows the definition following here. Now I'm going to prove that if the definition following Cauchy does not hold, then the definition following here also doesn't hold. So I'm writing approximately like this. Let A not be a limit of our function of x or Cauchy. So I'm writing down that the Cauchy's definition is false. I'm negating the Cauchy's definition. So I'm writing down there exists epsilon greater than 0 such that for a in delta greater than 0 there exists x from that deleted delta neighborhood of x0 such that f of x is not from epsilon neighborhood of a. So this is the negation of Cauchy's definition. Now, for any natural pattern, let delta be equal to 1 over n. And for this delta, so it says there exists such epsilon. Okay, very well. Now for any delta something happens. Now let delta be this number. This is a positive number. Now for this specific number delta, there exists a number x. There exists x. Since this depends on this size of delta, I will call it xn. So for different numbers n, for different natural numbers, they may be different x's. So there exists xn from this deleted 1 over n neighborhood of x0. So delta equals 1 over n, so instead of delta, we'll write 1 over n. There exists such xn, such that f of xn is not from epsilon neighborhood of a. Very well. So for any n, we constructed xn such that xn is from deleted 1 over n neighborhood of x0. Then a sequence xn is a Kane sequence at x0. So the distance from xn to x0 is less than 1 over n, and xn, so xn tends to x0, and xn does not attain x0 since it's from the deleted neighborhood. So this is a Kane sequence. Okay. Now, we know that there exists epsilon greater than 0, this epsilon, such that look, I have constructed this sequence xn such that f of xn is not from epsilon neighborhood of A. So I'm going to write it down like that. For any n at all, it follows that f of xn is not from epsilon neighborhood of A. Very well. Now, this is already a good enough statement, but I will fill it a bit to make it look what I want to make it look. So I'm going. This is true for any natural n, but I will write it like that. I will write it like that. There exists epsilon 0. So for a capital N, there exists a small n greater than capital N, such that f of xn is not from epsilon neighborhood. So I have written here a weaker statement. This bit is true for any n at all, for any natural n. But specifically, it is true for some small n greater than some capital N, whatever. This is still true. And this is, as you can see, this means that the limit of f of xn is not a constant. So our function so a is not the limit of our function over here. questions? Okay, so once again, I have proven that if some number is the limit of a function f following Cauchy, then it is the limit following Hebbian. And I have proven that if some number is not the limit following Cauchy, then this is not the limit following Hebbian. Okay, very well, very well. Now, could you tell me what was the definition that I gave you for the deleted neighborhood? Was there data or 1 over data? Deleted neighborhood. I want to know about the deleted neighborhood.
Дата.
Just data. Yes, one. Yes. Everywhere here, deleted neighborhood of x0 is deleted with the dot, and neighborhood of A is not deleted without the dot. Guys, I have realized that this proof would not work as smoothly for neighborhoods of infinity. So I'm giving you a new definition of neighborhood of infinity. Deleted neighborhood, deleted neighborhood of plus infinity. This will also be just neighborhood of plus infinity. And this will be a set of numbers 1 over delta to plus infinity. So, but basically I'm just putting 1 over delta instead of delta there. Since delta is a positive number, it kind of doesn't matter. I could put 1 over delta, it doesn't matter. But this way, my proof for this theorem works universally for all of the symbols. So delete minus. And delete it without sign. Without sign. Okay, guys, let's take a break. 5-minute break. If you have any questions, please ask for them. Okay, let's continue. Any questions? Now, we will have some theorems similar to those for limits of sequences. Let limit of f of x as x tends to 0 equals a at real limit of f of x tends to 0 equals real number b. X0 is real number. Then hey, there exists a limit as x tends to 0 of f of x plus g of x, and this limit equals 0. there exists a limit as x tends to 0, f of x times g of x, and this limit is a times. And there exists a limit as x tends to 0 of f of x divided by g of x, and this limit is a divided by b. Provided that the denominator doesn't turn into 0.
I think you have to write g of x.
G of x, of course. Thank you. G of x, thank you. This was a typo. Here it was g of x. Provided that b is not 0 and there exists a neighborhood of 0 such that for x from this neighborhood 0 g of x. Theorem. Let limit tends to 0 f of x equals a limit g of x equals b. If there exists a deleted neighborhood of x0 such that for any x from this deleted neighborhood f of x is less than g of x, then a is less or equal than and if f of x is less or equal to g of x, then also a is less or equal than b. I remind you, whether this is a strict inequality or not, the limits have not strict equality. So if the first theorem from today's lecture was theorem 1, let's call those theorems theorem 2 and theorem 3. Theorem 4. Let for any x from some deleted neighborhood of x0 actually less or equal. Let also there be a limit of f of x and a limit of h of x, and this limit we'll call a. It could be a real number or infinity. No, not infinity. Only real number, not infinity. Then there exists a limit over here x0, x0. Limits at x0, cos of 0. X tends to x0, g of x, and this limit also equals a. So this is a theorem similar to a theorem about 3 sequences, and we will call it a theorem about 3 functions. Proof of theorems 2, 3, and 4. Let's write down definitions of limits of all functions that we have in this, in those 3 theorems, using K's definition. statements of theorems 2, 3, and 4. Put 4. From corresponding theorems about sequences. This is not really a proof, this is a ideal proof, so this is the way to prove it. But I think you can see that this is obvious enough. So, for example, let's take this theorem number 4. Let's write down the definition of those limits following here. Yeah? Since we have this inequality, we have the same inequality for f of x and g of x and h of x n. Then, from the theorem of 3 sequences, we have that g of xn tends to the same limit a. By definition, following here, this means that the limit of this function is a. And exactly the same way it could be proved in the other 2 theorems. Okay. Next theorem needs proof. Okay. Theorem. Let y be equal to g of x and z be equal f of y. And since y is g of x, this would be f of g of x. Let there be a limit of g of x as x tends to x0. And we will call this limit y0. And let also be true that there is a neighborhood, there exists a deleted neighborhood of x0, such that for ax from this deleted neighborhood, it follows that g of x does not equal y0. Let there be a limit f as y tends to y0 of my function f of y. We will call this limit z0. So g tends to y0 as x tends to x0. F tends to z0 as y tends to y0, then there is a limit of f x tends to 0 and this limit equals 0. Let's prove it. So, I'm writing down Cauchy's definition. Yeah, Cauchy's definition of this limit. Limit of f of y equal to 0. So y tends to y 0 means for a epsilon equal to 0, there exists data equal to 0 for any y from deleted data neighborhood of y 0. It follows that f of y is from epsilon neighborhood of z0. This is just the definition. Now let's write down this definition. As x tends to 0, g of x is 0, same way. Now, here we usually use letters epsilon and delta as positive numbers. Now I'm going to use different letters. So instead of epsilon, I will use letter delta, and instead of delta, I will use a new letter. So for any delta greater than 0, there exists gamma greater than 0, such that for any x from deleted gamma neighborhood of x0, it follows that g of x is from delta neighborhood of y0. Okay, g of x is from delta neighborhood of y0, but we also know that g of x does not equal y0. But since g of x is not y0, we have that g of x is from deleted delta neighborhood of y0. It is from a neighborhood, but it's not y0 itself. Then this is from deleted neighborhood. Okay, that's all. Now let's combine it. So I'm combining those three statements, 3 lines. So for any epsilon greater than 0, there exists delta, and for any delta, there exists gamma. I will write there exists gamma greater than 0, such that for any x from deleted gamma neighborhood of G is from deleted delta neighborhood of y0, and since G is from deleted delta neighborhood of y0, like Rasim, hence y equals g of x is from deleted delta neighborhood of y0. Hence, from this line f of y, which is f of g of x, is from absolute neighborhood of z0. But this just means that there exists a limit of f of g of x as x tends to 0, and this limit is z0. Okay, that was theorem 5. Theorem 6. Cauchy's criterion. Existence. Of a limit. Similarly to Cauchy's criteria of existence of a limit of a sequence, we have a criterion for existence of an elliptical function. So let function f of x be defined in some deleted neighborhood of x0. There exists a finite limit of f of x, finite real number, as x tends to x0. And only if holds the next line, which is called the Cauchy's condition. Cauchy's condition. For any epsilon greater than 0, there exists delta greater than 0 such that for any points x1 and x2 from deleted delta neighborhood of x0, it follows that f of So this last line is called Cauchy's condition. Cauchy's condition. I need to prove it two ways. Necessity is if there exists this limit, then this Cauchy's condition holds, and sufficiency the other way around. Necessity. And let's put necessity. So let this limit exist. Let's call it a real number. Let's write down this definition. Here, once again using this trick, where instead of epsilon, I'm writing epsilon multiplied by some specific positive number. Since epsilon is any positive number, epsilon divided by 2 is also any positive number. Okay, so let's write down this statement for those two numbers x1 and x2. So we will have well, let's look over here. Let's look at this expression. F of x1 minus f of x2 is of course f of x1 minus a. And this is less or equal than f of x1 minus a plus x2 minus a. And this is less than. So x1 is some number from this deleted neighborhood, and for any number from this deleted neighborhood, this expression holds. So this first term is less than epsilon divided by 2, and similarly the second term is less than epsilon divided by 2, which is just epsilon. So for any epsilon, there exists data such that for any x1 and x2 from this deleted data neighborhood of x0. F of x1 minus f of x2 is less than epsilon. So this is